All right, so now let's take a look at the CDF. Let's take a look at the CDF, or derive the CDF for a uniform random variable with parameters theta 1 and theta 2. Remember, this is how we express the CDF generally, the cumulative distribution function. We usually use a big F, be a big G, or a big H, or whatever. And remember, we're indicating that we're thinking about this, the CDF for the random variable x. Okay? And it's a function of little x. So really this is a big X sitting in the subscript. This is a little x representing our sort of dummy variable that we might that we could fill a value in for. Okay? So this x here, just to remind you, this x here is that x, and this x here is that x. Okay? Alright, so how do we do this? Well, it's just the integral from negative infinity up to x of the density function. Alright, that's what it is for any continuous random variable. It's going to look like that. Now, for our specific one, this uniform random variable, what do we have? We have integral from negative infinity up to x of, and just drop in the density function there. It's 1 over theta 2 minus theta 1 times the indicator function of theta 1 being less or equal to x being less or equal to theta 2 dx. Okay. Now I want to think about the fact that there are really kind of three regions here. See, if x is less than theta 1, of course that integral is going to be 0, right? And if x is between theta 1 and theta 2, then I know I'll have some other kind of situation. And if x is at least theta 2, then I know that integral should be 1, right? If I think about that picture, 1 over theta 2 minus theta 1, right? Here is theta 1 and here's theta 2. This is what my density function looks like, right? So if my little x is over here, then what's the chance that this random variable falls at or below little x? It's 0, right? Because the density function is 0 there. So the integral up to there of the density function is 0. If I put x in here, then what's the chance that my random variable is less or equal to x? Then it'll be just the area to the left of x underneath this thing, right? If x falls over here, however, what's the integral of the density function to the left of there? Ah, it's 1, right? I know that because, look, this distance is theta 2 minus theta 1, isn't it? And then, so if I want the area of underneath this density function here, it's just the area of a rectangle, right? The height is 1 over theta 2 minus theta 1. So if I multiply this, the height, by the width here, theta 2 minus theta 1, I get 1, right? So then I know that this is going to be 0 for x less than theta 1, and it'll be 1 for x greater than or equal to theta 2, and it'll be something else for x in between the two. And I can tell you what that integral turns out to be. And so what you should verify this on your own, but that if x happens to be between theta 1 and theta 2, you should verify that this turns out to be x minus theta 1 over theta 2 minus theta 1 for x in theta 1 up to theta 2. Okay? Now that's a good way to write that, I think. A more succinct way, but maybe not quite as easy to read, I think. You could also write it like this. It's the minimum of x in theta 2 minus theta 1 all over theta 2 minus theta 1 times the indicator function of x being at least theta 1. Okay, so sometimes these indicator functions are real useful for helping us see things more clearly. Sometimes, if you write it more compactly like this, though, you sacrifice being able to see what's going on very easily. I think this is more easily the way it's written here is more easy to visualize, but this is certainly more compact. Do try to understand that this is equivalent to this.